Okay, here we go. Assignment 12.5, AB number 2. This is another multiple choice packet. So usually what I do on these is I will add some notes or we'll do some problems together, and then you'll try them and then I'll do them, and then you'll finish the rest on your own and check and fix them online. So here we go. Let's see. Just go ahead and just try, let's see, just try problems 1, 2, and 3. Pause the video and try 1, 2, and 3, and then unpause it and see how you did. Okay. So on the first one, it's asking about increasing, decreasing, and so forth. So that has to do with derivatives being positive or negative. And so you're going to want to find the derivative, which this one isn't too bad. And then you want to find critical points. So you want to set it equal to 0 or undefined, and factor it or whatever works. GCF x squared equals 4, square root of both sides, plus or minus. So this is plus or minus 2. Now, by the way, that's negative. Plus or minus 2i. So there's no real critical points, and we usually do like a line check next. We could still do a line check. There's just no critical points on it. We can still test a point. X equals 0. It's positive, so that means it's just positive everywhere, which means it's going up everywhere. It's increasing everywhere, so it's increasing for all x. Number 2, in which interval is the function increasing? So this is the same kind of problem. If you haven't tried it yet, try it. These aren't too bad. F prime of x, 3x squared plus 12x plus 9 equals 0. We could try and factor it. 3, take a 3 out. GCF will always make any next technique easier. Small numbers. X and x, 1 and 3. So x equals -1 and x equals -3. So then we would do a line check, and we'd put these on there, left to right, smallest to greatest. Test a point. X equals 0. It's positive, negative, positive. So increasing, decreasing, increasing. You can also use this to find relative maxes and relative mins. So we want increasing. So that's going to be -infinity to -3. And usually we include the endpoint for increasing, decreasing. Now, some of these problems I took from some other resource besides the College Board, so they don't, but they're not going to trick you on the AP test where they're going to put one with brackets and one with parentheses and make sure you pick the right one. So, and on free response, I think it'll be fine if you put parentheses in that kind of situation. Okay. Number 3, suppose that f prime, and f double prime are continuous for all real numbers and that f has the following properties. It says that these are all true. F is negative from -infinity to 6 and positive from 6 to infinity. It's increasing from -infinity to 8 and decreasing from 8 to infinity. It is concave up from -infinity to 3 and concave down from 3 to positive infinity. Of the following, which is the smallest numerical value? Which one's the smallest? What we might try and do is just first, I'm just thinking it just might help me kind of see what's going on better, is to maybe create kind of a number line. This is, so kind of going backwards with the line checks. And I think this will just help me. Let's see, increasing. So this is increasing and then decreasing. This is f prime. Then f double prime. It's going to be concave up and concave down. So it's positive there, negative there. Okay. So at f double prime of 3, is potentially 0, right? Because that's this inflection point. F prime of 10 is definitely negative, right? F prime of 4 is definitely positive. F prime of 1 is definitely positive. F prime of -7 is definitely positive. So which one is the smallest? Well, there's only one -1, so that one has to be small. So even without knowing specific values, we're able to, compare those. Okay, I want you guys to try problems 5 and 7 right now. So just pause the video for a second. Try 5 and 7. And then unpause it and we'll do them together. 5 and 7. So number 5, how many points of inflection? Just how many points of inflection? So we need to get the second derivative. So 12x to the 5th plus 45x to the 4th plus 40x to the 3rd minus 1. And then the second derivative is going to be 60x to the 4th plus 180x to the 3rd plus 120x squared. We're going to set it equal to 0 or undefined to find potential inflection points. Let's see, we could factor 60x squared out. So then there's going to be x squared plus 3x plus 2 left over. And then we could try and factor this, plus 2 plus 1. Now, we still have this x squared here. Don't lose that. So x equals 0, x equals -2, and x equals -1 are places where we might get an inflection point. But you guys should, we don't need to do a line check for this. We could if we wanted to figure out where it's concave up and concave down really quickly. But if we're just looking for which ones are inflection points, we don't need to do that because concavity has changed signs. And usually that happens at a 0 for any kind of function. Unless it's raised to an even power, then it kind of bounces off the graph. That's like a double root or an even power. So these two are the inflection points. So it has 2. We don't need to do anything else. Now, if we did want to find where is it concave up or concave down, we'd put these all on here. Don't forget, test x equals 1. It's going to be positive, it's going to stay positive, and then it's going to go back to changing. Now, this is concavity, so I draw these little symbols here. So this is concave up, concave down, concave up, concave up. Now, if you were doing concave up, you got to be careful. You have to split it up at 0 because concavity is 0 there, so it's not concave up there. Should have tried number 7. They give you a graph and it says that it has an inflection point. What is the value of b? Well, if it has an inflection point, then most likely its second derivative is 0 undefined. So we take the first derivative, 3x squared plus 2ax. A and b are just constants, okay? Plus b. And then we take the second derivative and we get 6x plus 2a. And we set it equal to 0. Now we're trying to find b specifically. Now, be open to the idea that we might find a first, but also realize that answer is probably in the list because that's how tricky multiple choice questions can be. So now we know that this is the point we're interested in, x equals 2. So we're going to plug 2 in here. And we're going to get 2a equals -12, and we're going to get a equals -6. Now, that's the a value. So then we still need to find the b value. So how do we find the b value? Well, we have this original function, by the way, remember? And we have an xy pair that goes into it. So we could plug in y into that and x2 into the x's. We just found a is -6. So we've got to use that. X is 2, b We don't know. That's the thing we're looking for. X is 2 minus 8. So now we have an equation with one unknown. So we should be able to find this. So 0 equals 8 minus 24 plus 2b minus 8. 2b equals 24. B equals 12. So kind of tricky, little bit of solving like systems of equations and stuff on there. Algebra's a little tough. Okay, let's go to the next page. And I want you guys to try a few problems here. I want you to try, I guess let's just start with just trying 9. So pause the video for a second, try 9. So on number 9, we're looking for relative minimums. So a bunch of these problems are going to be relative min, relative max problems. So we probably want to use first derivative test unless we can for some reason. Then we'll use second derivative test. We often like to do line checks if we have the actual function. So first thing we need to do is find critical points. 4x cubed minus 16x, set it equal to 0 undefined. Factor a 4x out, x squared minus 4, x plus 2, x minus 2, 4x. So x equals 0, negative 2, and positive 2 are your critical points. So then we'll do a line check. None of these have even powers on them, but you should always think about that, check that, put these in order left to right. Test a value, x equals 3. I like to test far right because it usually makes everything positive, which is quick and easy. So it's positive, negative, positive, negative. So down, up, decreasing, increasing, decreasing, increasing. So this has a lot of information, but it has right here, this is a relative min, and this is a relative max, and this is a relative min. Now, the values there aren't the relative maxes mins. The relative max and min would be the y value that you would get by plugging these back into the original function. These are the x coordinates. These are the locations. So the relative min is at negative 2 and 2. And we're just looking for minimums. So I want you guys to go ahead and try 10, 11, and 12. 10, 11, and 12. So pause the video and try 10, 11, and 12. So number 10, we're looking for relative min. This is your function. So we got to take the derivative, 24x to the 5th plus 24x squared, derivative 18 is 0, set it equals 0 undefined. Factor it, 24x squared GCF, x cubed plus 1 left over. So x equals 0 and x equals negative 1, because you take cube root and that's fine. This one has an even power on it. So these are your critical points. Do a line check. Negative 1, 0. Test a value. X equals 1. Positive, positive, negative. Decreasing, increasing, increasing. And this is a relative min, and this is neither. So we're looking for relative min. What values of x does it happen? It's at negative 1. And you got to be careful. Sometimes they could ask you for the y. 11 is a graphing calculator problem, which should be helpful because that would be ugly. It'd be a lot of ugly work. FDT function, and they're giving you the derivative. How many relative maximum points does it have? On 0 to pi. So if we go in here, we could put this in your x over 15 plus sine of e to the 0.2x close, close, go to window, go to 0 to 4 pi. We don't really need to see the whole graph of this. We kind of just want to see the x-intercepts, but we could see the whole graph. We could go, after you enter the x window, even though we don't really know how tall this graph is going to be, we could go to zoom 0. Sometimes this can backfire on you. If you get some really big values in a graph, it'll just make the graph really huge. But this seems reasonable. So I'm just going to sketch this. Not that you would during the AP test. Just, if you felt like you could figure out what the answer was just by looking at this. But this is the derivative, by the way. So if you're like, oh, relative maximums here and here, nope, those are not relative maximums. Those are actually inflection points because that's where the derivative of the derivative changes sign, okay? This is a critical point. This is where f prime equals 0. So this is the graph of the derivative. So we do this a lot, graph of the derivative. And here it's positive increasing, negative decreasing, positive increasing, negative decreasing, positive increasing. So it's going up to down. This is a relative max. Down to up, down to up. This is a relative min. And if you're going up, you hit a flat spot and then you go down. That must be relative max. And this is a relative min, down then up. They said, how many relative maximum points do you have? So we have one there, one there. We have a total of 2. So that's how you can use your graphing calculator and also your knowledge of graphs of derivatives to answer that question without actually finding the specific values. Number 12, the maximum value. Now, the maximum, that means absolute, okay? And so we should use extreme value theorem. Anytime we're looking for absolute maxes or mins, we should use extreme value theorem. So f prime of x equals 6x squared minus 18x plus 12 equals 0 undefined. Got to find our critical points. We're going to factor 6 out, x squared minus 3x plus 2. That just makes the number smaller for factoring or whatever approach you have to use. So x minus 2, x minus 1, give you positive 2 and negative 3 in the middle. And so x equals 2 and 1. Those are our critical points. Then we need endpoints. These are our endpoints. So you can only use absolute extreme value theorem if you have a continuous function, which this is, on a closed interval. That means you have to have endpoints. So then we usually make a table here. And we got to plug these back into the original equation. And we put the endpoints and the critical points. Now, if any of the critical points fall outside the endpoints, don't calculate them. So we're plugging these in here. That's going to be negative 2, minus 9, minus 12, minus 1 equals negative 11, negative 23, negative 24. If you plug positive 1 in, you get 2 minus 9 plus 12 minus 1, which should be negative 7, 5, positive 4. Plug 2 in, you're going to get 8, 16 minus 36 plus 24 minus 1. That's going to be negative 20, positive 4, positive 3. And we're looking for the absolute max value right here. Now be careful, because some of you guys are going to be like, oh, there it is, it's 1. It says, what is the max value? They're looking for the y value here. So for response questions, I just write really nice, thorough answers. Say the absolute max value is 4 at x equals 1 by extreme. Okay, and then I'm covered all the time. But a multiple choice, you got to pick one or the other. They wanted the y value. This is the answer. Okay, so be careful. There's a couple more problems like that you guys can do later. Let's look at 15. And I don't know, go ahead and try it first, I guess. And then, so just pause the video for a second and try number 15. Okay, so it says let the function B find all the values of C that satisfy the conclusion of the mean value theorem on the closed interval. So the conclusion is the C value is the place where the actual value equals the average value. Now, this could be for original function or for the derivative. So I guess we could try one or the other. We could just try the regular mean value theorem. So here's a good opportunity to try and see if you remember the mean value theorem without having to look at your note sheet. So it's the average y value, the average height. So we take the curve and we take the area under it and we smooth it out. That smoothed out curve is the average height of the whole original curve. The area under the smoothed out curve now looks like a rectangle, but it's the same area that we started with. And so if we take that area and think of it as a rectangle and divide by its base, then we will get its height, right? And that's what we're looking for. So antiderivative of x cubed is x to the fourth over 4. You got to plug the limits in. So we're just trying to find the average value first and then find the C value, okay? So this is going to be 16 over, so this is going to be 1/3. That's going to be 16 over 4 minus 1/4, which is going to give you 15/4, right? 15/4, which is going to give you 5/4. So that's the average value. And now we're looking for the C value. So you set the original function equal to the average. So we set x cubed equal to 5/4 and we solve. And so we get x equals the cube root of 5/4. And this value should be between or on the endpoints. Now I don't see that value here. So maybe we were supposed to do mean value theorem for derivatives. So this is just a good opportunity to review these ideas again real quick. So mean value theorem for derivatives say that if you're trying to find the average of a derivative, it's just the slope between the endpoints. Rise over run, change in y over change in x. Now, you can get this relationship by plugging the derivative into this, and you'll eventually get to here, but it's a little quicker if you know you're dealing with the derivative to just jump into the slope of the secant line connecting the endpoints. If we plug 2 into that, we get 8. If we plug -1 in, we get -1. And so that becomes plus. And so we get 3 for f prime average. So then we set that equal to f prime in general. So f prime in general is 3x squared. And we set it equal to 3. And we get x squared equals 1. And then we take the square root of both sides, plus or minus. And it could be either one. And we're going to go with just the positive value because the negative value is on the edge. And because it's derivative, we're going to exclude that. So we're going to go with 1 only. All right. Let's see if we can try a few more of these. Let's see. Average rate of change is the way they like to usually refer to f average, f prime. By the way, on the AP test, average rate of change. I'm going to let you guys do these on your own. Let's jump to 18. 18, 19, and 20 involve related rates, it looks like. And it's been a while. So let's see if we can remember how to do those. The radius of a sphere is increasing at a rate of 2 inches per second. So what I would do is I'd write that as a calculus expression, calculus relationship. The radius of the sphere is increasing. That's dr dt at 2 inches per second. And I know it's dt because it has time in it. How fast in cubic inches per second is the volume increasing when the radius is? So we're trying to find dv dt, the derivative of volume. Increasing means it's derivative. Trying to find that when R equals 10. So I've taken all these words and summarized them nicely. Now, to do related rates, you usually are given a rate of something and you need to use it to find a rate of something else. So then the first thing you need to do is figure out, well, how do I relate those two variables without the derivatives first, the V and the R? And so this is a sphere. So the volume of a sphere is 4/3 pi r cubed. Might be a little hard to remember. And then we're going to take the derivative of it implicitly with respect to time. And we say implicitly because there are no t's anywhere. So the derivative of volume is going to be dv dt. And here, 4/3 and pi are just constants. We get a 3 out in front. So it's 4 pi r squared. That's the outer derivative. And then we got to take the derivative of what's inside, dr dt. Which, by the way, if you don't do and you don't use this thing they gave you, you should probably be worried. I mean, sometimes they give you information that you don't need, but usually you need it. So we can now plug in 10 for R and 2. Now be careful with any rate that you are plugging it and substituting in or getting to think whether it should be positive or negative. And up here it says that the radius of the sphere is increasing. So the other thing that I'm always super careful on related rates is to put positive or negative in front of my rates. And then whenever I plug them in, I put the positive or negative. Because it's easy to forget and it's an easy mistake to make. Because if they said decreasing, they're not going to put negative in what they give you. You need to put negative in your work. So this is going to be 200, 800 pi cubic inches per second. Because it's volume, which is 3-dimensional, over time. Why don't you guys try problem 20? Pause the video, try problem 20, and then we'll do it together. So problem 20, the volume of a cube. Volume of a cube. Now what's the volume of a cube? Side cubed is increasing at a rate of dv dt. The volume is increasing at a rate of 20 cubic centimeters per second. How fast in square centimeters per second is the surface area of the cube increasing at the instant when each edge is 10 centimeters long? Okay, so that's all the information they've given you. We have dv dt, and we need to somehow relate to ds, the surface area. Now, there isn't a direct equation involving volume and surface area. So what you probably need to realize, well, let's start with surface area. Surface area is, for a cube, you can draw a picture if you want. There are 1, 2, 3, 4, 5, 6 sides, right? And they each have an area of side squared. So the surface area is 6 times side squared. And if we wanted to take the derivative of this, I mean, this is the formula for surface area, we get 12s ds dt. Now we have s is 10, but we don't have ds dt. We have the volume. Sometimes what you have to realize on related rates is they give you another rate. To find another rate, that is what you need. We need ds dt to finish this problem. But volume of a cube, which we just wrote, was s cubed. So dv dt is 3s squared ds dt. So this has what we need in it. The volume is positive 20. dv dt is positive 20. We can plug 10 in here for the sides. So that's going to be 300. So ds dt equals 20 over 300, or 2 over 30, or 1 over 15. So over here, it's going to be 12 times 10 times 1 over 15. So that's going to be 8. Okay. Last page. Let's see if I'm going to do these with you. Why don't you, let's see, try 21 and 22. 21 and 22. And then we'll do them together, and then you'll finish the rest on your own. 21 and 22. So go ahead and pause your video and do 21 and 22. Now, 21 shows the graph of f double prime, the second derivative of the function. The function f of x is continuous for all x. Which of the statements about f are true? Is true. So they have to be true. F is concave up from x less than 0 and from b to c. Yes, some people would think, oh, that's concave down there, but these are f double prime values. So this represents concave up because they're all positive. This represents concave up because they're all positive. This represents concave down. I can see people saying, no, that's not true. That's true. F has a relative minimum in the open interval b to c. So does it have a min somewhere between B and C? All we know is that it's concave up the whole time, which could have a minimum. Definitely not a max. But we don't know if it's like that. We don't know if it's like that. I mean, it goes from concave down to concave up, but does it go from concave down to concave up like that? I mean, it could have a min. We don't know. It could. Don't know, but it has to be for sure true all the time. F has inflection points at 0 and B. It's going from up to down, down to up. That is true. So the answer is 1 and 3. So these Roman numeral problems are kind of annoying because there's like 3 problems in one, and you got to get all 3 problems right to get the credit. 22, the table above gives the values of the derivative f prime. Based on this information, it appears that in the interval covered by the table, f is increasing and concave up everywhere. F is increasing and concave down everywhere. F has an inflection point. F is decreasing concave up everywhere. F is decreasing concave down everywhere. So the first thing to look at is that all of these are positive. So that this is derivative. So that means it's increasing everywhere. So I'm going to go with increasing, increasing, not decreasing, not decreasing. Just process elimination. Now, concavity is the derivative of the first derivative. So let's just look at what's happening with the concavity. The changes. Just plus 0.015 plus 0.015 minus 0.005 and then minus 0.015. So I would say this is like concave up because the derivative is increasing. The derivative of the first derivative is positive, and this is concave down. So I don't think it's for sure not concave up everywhere or concave down everywhere. So those are out. It must have an inflection point if concavity changes. So I guess we're down to C, right? We eliminated all those others. All right. We're done with the video. You guys can go ahead and finish this. Check your answers online, fix them, and turn it in.